Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and in this 4th semester there is a paper on basic physics 2 which contains several chapters, and the first chapter is on optics. In this chapter the contents are defects of images, spherical aberration in mirrors and lenses, and method of minimizing spherical aberration, and so on. And we have been seeing in the last few lectures the salient features with regard to this area, the topics I mentioned. Let us today recapitulate some of the important things which I have told in the earlier lectures. So, we are discussing about defects of images, and is lecture number 5. This section on defects of images is of great significance, because the images that you capture through a camera or a telescope or a microscope, the images that you obtain are somewhat defective. They are different from what you should have actually got. Compared to the actual image, the image that you obtain is somewhat defective. In the first lecture, I showed the image obtained by Hubble's telescope of the stars and other things in the sky, and great scientists like Newton and Galileo, they made the first terrestrial telescopes, and they encountered several problems with regard to spherical aberration in mirrors and lenses. And so, when you want to capture the image, or when you want to see a distant star, as was done by Newton. So, Newton had the Newton's telescope, and Galileo made his own telescope, and these people, the great giants, they encountered problems because of spherical aberration which is produced by mirrors and lenses. And therefore, we are going to see in today's lecture how the defect, namely spherical aberration that we have, can be minimized, and what are the methods which could be adopted. And so, the contents will go as follows: a review of defects of images, spherical aberration in mirrors and lenses, methods of reducing spherical aberration in mirrors and lenses. I told you in the last lecture what is meant by spherical aberration in a case of a spherical mirror. You have got a aberration in mirrors, and in a spherical mirror of this kind, you see the optic axis here, right. This is the optic axis which passes through the center of the mirror, and this is the point C refers to the center of curvature, and this is the focal point. F is the focal point here, and you see all the light rays do not pass through the same focal point. What you observe is the marginal light rays. What I mean by marginal light rays, that you should have understood by now, the light rays which are hitting the mirror far away from the optic axis. This is the optic axis, right, away from or at the margin or at the regions which are away from the center. They are the marginal light rays, they are reflected in this direction, and similarly this is reflected in this direction, right. So, the marginal light rays will be getting reflected and come to a focus at a point nearer to the mirror, whereas the paraxial light ray, this is a paraxial parallel to the optic axis. The light ray parallel to the optic axis is called the paraxial light ray. The paraxial light ray will come to a focus somewhere here, whereas the marginal light ray will be getting reflected and it comes to a focus nearer to the center of the mirror. So, you should understand the marginal light rays will be reflected and will be passing through the optic axis at a point nearer to the center of the mirror, whereas the paraxial light rays which are nearer to the optic axis will be reflected and they will be passing through the optic axis at a point away from the center of the mirror. Okay. So, the two foci will not coincide. I will show in the next picture where you find the focal points. As I told you, the marginal light ray is here, that comes to a focus here, right, nearer to the mirror, whereas the paraxial light ray comes to a focus somewhere here. Therefore, you get two focal points, as a result of which what will you obtain? You will be obtaining or you will be observing a blurred image. You have got the image produced is blurred, and in order to obtain a perfect image, what has been done is you have to reduce the curvature, you have to change the curvature. Instead of a concave mirror, what people have observed is, instead of a spherical mirror, if you use an elliptical mirror, this particular aberration can be reduced, or you try to cut the light rays. You can use what are called stops, as I showed in the last lecture, which I will be repeating to a certain extent in today's lecture, or also how the aberrations produced by mirrors as well as lenses can be reduced to a large extent. But remember, the image that you obtain through a camera or a telescope or a microscope, the corrections, the defects that you observe, the defects that you have cannot be completely eliminated. As I told you, the defects are due to the spherical aberration, chromatic aberration, astigmatism, coma and distortion. These are the various defects with respect to images. There are various causes which lead to the defects, and I will repeat once again, the defects of images are classified under the following categories, namely spherical aberration, chromatic aberration, astigmatism, distortion and so on. Therefore, you have methods by which these defects can be minimized, or spherical aberration, for instance, can only be minimized, it cannot be completely eliminated. None of the defects which I mentioned just now can be completely eliminated. By different methods they can be minimized, and in today's lecture I will be talking about the different methods. One of them is using what are called stops, and as I told you, in the case of mirrors, you have got the two focal points, right, one nearer to the mirror and the other one slightly far away from the mirror. There are two focal points leading to a blurred image, and this is a perfect image. Similar to the case of a mirror, in the case of lenses also, you have got one focal point here, which is again due to the marginal light rays. Similar to the case of mirror, in the case of a convex lens also, the light rays which are incident at the margin means at the peripheral region of the lens. This is the central region, right. This is the peripheral region at the edges. When the light rays which are incident on the edges, they undergo refraction and they come to a focal point which is nearer to the lens, whereas the paraxial light ray, that is the light ray parallel to the optic axis, it comes to a focus point far away from the lens, the center of the lens, and this is called IP. IP is the image which is produced by paraxial light rays. P stands for paraxial light rays, whereas M stands for the marginal light rays. Therefore, similar to what I showed here, in the case of mirrors, the light ray which is due to the paraxial thing comes to a focal point nearer, whereas the light rays which are these are paraxial light rays, the marginal light rays. The marginal light rays will come to a focus nearer to the mirror and also nearer to the lens, whereas the paraxial light rays will be coming to a focus far away from the mirror or the lens. As I show here, in the case of a lens also, the paraxial focal point will be away from the focal point that you get from the marginal light rays. Now, this AB is the place where if you put a screen, you get what is called circle of least confusion or the best possible image. This image will be blurred, this is also blurred, and the best possible image is the one that you obtain when you keep the screen along AB, and you talk of circle of least confusion and so on. And the one possibility is to cut the light rays. That is what you are going to do now. This is once again which shows the spherical aberration produced by a convex lens. You see a focal point here, a focal point here, and light rays, optic axis is shown here. The best focus is the one that is obtained here, that is similar to your AB. The AB is the region where you get the best focus, or it is called the circle of least confusion. You got a circular image which is much clearer compared to what you get at IM and IP. So, this is the best focal point. You have the best focal point here. This is the marginal focus, this is the paraxial focus. Okay. So, you can make use of what are called stops. As I told you in the last lecture also, in the case of a spherical mirror or a lens, you can cut the light rays which are going in this direction or which will be incident at the peripheral region, or the marginal light rays can be cut off. You try to remove the marginal light rays using stops. Stops are nothing but they are stopping the light rays which will be incident on the peripheral region, or the so called marginal light rays are cut off. As a result of which you will be getting a better image, but what will happen is, because the light intensity is reduced, you are cutting a portion of the light ray, the image that you obtain will be of lesser intensity. Okay. So, the aperture blocks out rays that blur the image. The disadvantage is, however, a greatly reduced light throughput. That means, the intensity that you get here for the image, even though it may be clear, the intensity will be somewhat lesser if you are cutting a portion of the light beam. That portion that can be cut either can be the marginal light rays, or you can keep the stops here, so that the paraxial light rays can be cut and allow only the marginal light rays. In either case, you will be getting a clear image, but the intensity will be poorer because of the fact that you are cutting a portion of the light rays. So, that is what I told you in the last lecture. The stops can be used. Because I am reviewing, let me not spend more time on the stops, which I have already done. And secondly, you can make use of a lens which has a radius of curvature R1 and the other face will have a radius of curvature R2, which will differ by a large amount and which will reduce the spherical aberration. I am going to now, let me not go through the mathematics because I have done it earlier. I will find out the condition for R1 and R2, so that your dx by dk is 0, or the condition to be met is the following. As I told you just now, you have to choose a lens such that the radii of curvatures, you have got R1 here, R2 here. R1 is the radius of curvature of this lens, R2 is the radius of curvature of this surface. You have got the same lens. The two surfaces have got differing radii of curvatures. One is R1 and R2. What about R1? R1 forms, as I told you, a portion of a circle in a 2 dimension. You can complete this, right, a circle, and you know the shape is such that R1 will have a smaller radius of curvature, whereas R2 is somewhat planar, right, compared to this surface. So, R2 will have a bigger radius of curvature, right. It forms part of a circle, and for R2 the radius of curvature will be larger. So, you choose a lens such that your R2 is 6 times R1, or R1 by R2 is 1 by 6. That means, R2 will be 6 times R1. The R2 that you have got here, the radius of curvature of this surface should be 6 times that of this surface. If it is so, the spherical aberration can be minimized to a large extent, provided you assume the refractive index of the material of glass. The material that you are using for a lens is 1.5. In the relation that you have got here, if mu is 1.5, then what you find is your k will be equal to minus 1 by 6. In other words, the conclusion is the following. Thus, the lens which produces minimum spherical aberration is a lens whose radius of curvature of one surface is 6 times the radius of curvature of the other surface, or in other words, one surface should be 1/6 of the radius of curvature of the other surface, okay, and vice versa. Okay. That is the conclusion. So, if you are using plano-convex lenses, again the spherical aberration can be minimized, and the spherical aberration is due to what? Is the result of a larger deviation of the marginal rays compared to the paraxial rays, because the marginal rays and the paraxial rays do not come to a focus at the same point. Now, we go through the following facts. If the deviation of the marginal rays is made minimum, then the two foci will come closer, reducing spherical aberration. The spherical aberration produced by a single lens can be minimized by choosing proper radii of curvature, and you come across what is called a shape factor, and the shape factor is defined as follows. Q is equal to R1 plus R2 divided by R2 minus R1, where R1 and R2 are the radii of curvatures of the two surfaces of the lens. And now, we have a graph drawn between the shape factor taken along the x axis and the axial spherical aberration drawn along the y axis. So, you have to calculate the axial spherical aberration as a function of shape factor. You have to calculate the shape factor by giving various values, right. You have the shape factor q is a function of R1 and R2, that divided by R2 minus R1. So, the shape factor, as it varies from minus 2 to plus 2, the spherical aberration will have values starting from 0.1 to 1.0 here, And the important point to be noted is the spherical aberration is a minimum when x is equal to 0.5. When the shape factor q is equal to 0.5, you have got 0.5 here, the spherical aberration is found to be minimum. And so, spherical aberration for a double convex lens with shape factor is equal to 0.5 is a minimum when the surface of smaller radius of curvature faces the incident parallel light. So, and also you can make use of plano convex lenses can also be preferred. Spherical aberration can be made minimum by using two plano convex lenses separated by a distance d. Supposing you got f1 and f2 as the focal lengths of the lenses, then the condition for you got two plano convex lenses. Remember, you got two plano convex lenses separated by a distance d. What is f1? f1 is the focal length of the first lens, plano convex lens. f2 is the focal length of the second plano convex lens, and these two lenses are separated by a distance d. Then the condition for minimum spherical aberration is the following: d is equal to f1 minus f2. So, by a suitable combination of convex and concave lenses, spherical aberration can also be minimized. Combining a concave lens with a convex lens, also the spherical aberration can be minimized, and again spherical aberration can be minimized by what we call as axial grin lenses, about which I will talk in a later lecture. So far we have been talking about spherical aberration which is produced by mirrors and lenses, wherein we make use of a monochromatic light. What do you mean by monochromatic light? Light of a single wavelength. For instance, you all know by now, is it a monochromatic source? The light source that is coming from a mercury vapor lamp, is it a monochromatic source? It is white light. It consists of different colors, as all of you know, in the order of VIBGYOR. So, this is not a monochromatic light. White light is not monochromatic because it contains several wavelengths starting from violet to red. Now, can you tell me what is a monochromatic beam? You could have done Newton's rings or the experiments on air bridge and so on. The sodium vapor lamp, which emits light of wavelength 90 or 96 angstrom unit, right? It is a doublet, sodium doublet 90 and 96. You all know by now the light coming from a white light like the mercury vapor lamp is not a monochromatic source, it is white light. On the other hand, light coming from a sodium vapor lamp is a monochromatic light beam, because its wavelength can be taken as 5893 angstrom unit. Now, we are talking about what is called chromatic aberration. Chroma means color. Chromatic aberration is a defect which is produced when white light is incident on a lens. Assume a lens, when white light is incident or passing through a lens, then you get what is called chromatic aberration. By chromatic aberration, what you observe is the, instead of getting a single focal point, you get the image, a spread out image from violet to red, because the white light consists of all colors. The image also will be spread out from violet to red. It is interesting to see this is caused by variation of the index of refraction of a lens, with the wavelength of the incident light. All of you should be knowing that the refractive index is a function of a wavelength, right. Refractive index is a function of the wavelength. It is in addition to all the other aberrations discussed earlier, which are caused by the inadequacy of the paraxial ray approximation and have nothing to do with the color of the incident light. It is the paraxial approximation that we have made use of in obtaining the relation connecting the object distance, image distance and focal length. That is what you write 1 by f is equal to 1 by u plus 1 by v, and this is called the paraxial approximation. But on the contrary, you have got the marginal light rays also, and that is the reason why you have the defect, and this is a chromatic aberration. What you observe is, you assume this to be white light. When the white light is incident, when white light is passing through a prism, you assume this to be a prism, right. You take this portion, you assume this to be a prism, and when white light is made to pass through a prism, what happens? You all say that you observe what is called dispersion. What is meant by dispersion? The white light is split up into the colors in the order of Vibgyor. Vibgyor means the all colors starting from violet to red. It was observed by Newton by using a prism. The white light can be split up into its constituent colors. The colors will range from violet to red. So, also now the light ray is incident here. So, you will be it gets split up, right. You see it gets split up, and violet comes to a focus here, whereas red comes to a focus here, right. Because the refractive index is a function of the wavelength, and the wavelength of violet and red are different, right. So, the refractive index of violet and red will be different. You have all studied dispersive power. The dispersive power is a function of mu v and mu r. You write dispersive power omega is mu v minus mu r by mu minus 1, where mu v is the refractive index of violet light of the lens, whereas mu r is the refractive index of the red ray for the lens. So, when you have a lens, the refractive index for the different colors or different wavelengths will be different, and as a result of which violet will come to a focus here, red will come to a focus here. So, a white light will give us an image here, right, a linear image. You got a image starting from here violet to red. The violet rays will come to, the white light will be getting split up into different colors. The violet ray will come here to a focus, the red ray gets focused at this point. So, you have got an aberration. You are getting a point image, you get a blurred image or a line is obtained, and that is the so called chromatic aberration. Let me now pass on to the summary session. It goes as follows. There are several methods of reducing spherical aberration. One is stops can be used, or choose a biconvex lens such that R2 is 6 times R1. For two plano-convex lenses separated by a distance d, the above aberration can be reduced if d is equal to f2 minus f1. Lastly, chromatic aberration is produced because of white light. We have the following questions for you now. The first question is, what is meant by shape factor? What is the condition under which two plano-convex lenses separated by a distance will lead to minimum aberration? Comment on the radii of curvature of the convex lens to reduce spherical aberration. Lastly, what is meant by chromatic aberration? with this we come to the end of the lecture 5, and in the next lecture we will discuss in detail chromatic aberration and how this chromatic aberration can be minimized using what are called achromatic lenses. Thank you.